with lecture 14, shortest path special cases. Okay. But before we get to the material, let's talk about quiz 2. So here's the distribution for quiz 2. When the TA saw this, they were like, "Oh man, the students are giving you the middle finger." It looks like that. Okay, so let's go through this. It's out of 60. So if you're getting like 50 to 60, you're doing a good job. Like, keep it up. If you're getting above the 35, there's room to improve. You're doing okay, but I think there's room to improve. If you're getting below 35, I think you want to take action now. Okay, so the way you take action is by reaching out to your TA, reach out to me, post questions on Piazza. Okay, please do something. All right. There are two special cases, and I haven't graded these yet. They took the exam slightly after. I'm almost done. Okay, so this is not that they get 0, that they just haven't been graded yet. So if you look at the specific problems, actually, you guys were doing quite well for problem 1 and problem 2. The major difficulty was in problem 3. Okay, so let's talk a little bit about problem 3. Problem 3 was LCA, which is the lowest common ancestor, and we discussed this before, so I won't go into details. But I want to point out like the major errors. Okay, the major error is this. A lot of students assume that a parent pointer existed when the instructions in the question specifically says the notes don't have parent pointers. So if you say find parent, that's fine, but you have to take that into your time complexity analysis. But a lot of people just say traverse up the tree. You cannot traverse up the tree unless you have parent pointers. Okay, so that's something to do. The second is that a lot of students assume that the problem had the tree was always a binary search tree. But if you look at the next line, it says your method should work on any binary tree and not just binary search trees. It's very important. You have to read the question carefully. Okay. There is a difference between binary trees, binary search trees, and balanced binary search trees. Okay, so you have to keep those differences in mind. A binary tree is just a tree which has two children, classically. Binary search tree has this additional property that what? Everything in your left subtree must be less than a node, everything in the right subtree must be greater than a node. And balance means that it's height balance, right? For example, in ABLs or red trees. So please keep these differences in mind. If you don't know the differences, it will be very hard to answer the questions for you. Again, please read the instructions very carefully. If you don't read the instructions carefully, you'll be likely to see an error. Okay, so please read the very carefully. Alright, so that's your grades. This is my grades. So remember I asked you to do a mid-semester survey. I do this every year, and we try to take your feedback into consideration. So this is how you're finding lectures. Most students are finding lectures okay, but there are a proportion of you that are finding just okay. I mean, like good, nice. Just okay, and then some of you are finding slowly. And I really try to avoid this. Right? It's a good thing that no one shares this, but this is not great either. So I think that there's USB 3. The first is a speed check. So there were a whole bunch of comments. So I read through not only the stats, but I looked through everybody's individual comments. Right? So the first major complaint is that the lectures were too fast. Right? So sometimes the students discuss too quickly miss, pace too fast, slow the pace by a little, especially the parts. Okay. A lot of the students, one of you gave a very good suggestion, which was to include the question polls online during lecture for you to ask questions. So this will just slow down the process. So agree, okay, I'll slow down, but I need your help to slow me down. You have to be the cop here, okay? You have to tell me if I'm going too fast, right? Yeah, because I can't tell sometimes, right? Because some of you are nodding and some of you are sleeping, so I can't tell all the time. You need to tell me if I'm going too fast. And the way we do this is via the online polls. We'll do that today, starting today, okay? Alright, some people are still asking for webcasts. I don't know why, because the webcasts are already up. But maybe it's not fast enough. So I'll try to release the webcast faster. The reason why they're a bit slow is because I go through all the webcasts first and I notice I edit them and make sure that I say something wrong, I correct it in the webcast. Okay, so that's why the webcast take a little longer to come out. There is a couple more comments about the heaviness of the course. So 2040S has a bit more material than 2040. The reason is that I don't like to dumb down material. I think that I'm doing you a disservice if I make the material too easy. Alright? I mean, when you go out there to the real world, when you compete with other people, not from NUS, right? You're going to be competing against people from some of the top universities, and they're going to learn a lot more stuff. They'll be knowing a lot more stuff than you do. Okay, so when I ask my PhD students, for example, what do you learn in data structure and algorithm in your university, wherever they're from? And I consistently hear that they learn a lot more things than the students here are exposed to. So I'm trying to change that. I'm trying to increase the level of amount that you're exposed to, so that when you go out there and you're asked to solve problems, you're able to do it efficiently. Okay, so that's why we're introducing a bit more content in the usual. Alright? Somebody did ask me to tell me how to answer your exam questions. I cannot give you the answers in advance, but we do cover exam questions after, so that's what we say. Okay. So about problem sets, most of you are finding problem sets are good, right? Some of you are finding it not so okay, and some of you have not done problem sets. Please do your problem sets. If you don't do your problem sets, it's kind of hard for me to, kind of hard for us to help you learn. Okay. There are some complaints about the problem sets. Some people are saying it's too difficult and placed at the wrong times. So someone is commenting that it's placed on the week to exams or submission dates. Sometimes some people are saying that we should release after we learn the concept, not before or during. And that we should have a spectrum of difficulties or closer to what you're learning. Okay, so to me it's a little surprising. So how we design, we don't simply pick problems when we are talking about what to include for the next concept. The way we do this is we actually organize it so your concept should take no more than 4 to 5 hours. Okay, that's our target. I know it takes you longer, but that's what we envision, right? It should take you no longer than 4 to 5 hours. We include 2 to 3 easy or medium problems and 1 like easy problems.
4 to 5.
They are always based on a video cover. So if you see that you're required to do something very outlandish, usually you're on the wrong path. Okay? They always are based on things that you've already seen or will see in the week that the problem set is released. Now, why can't I always have it after you learn the concept? It's because the timing is 2 weeks. So I cannot spread it out too late, or else you will only get the problem far too late and then it will be heavy towards the end. Alright, I'd rather have it heavy a little bit at the beginning. So you have 2 weeks. This is always why I insist that students start early, but this never happens. But please start early. I keep repeating this. Please start early. 2 weeks is as long as I can make it. I can't make it any longer. 2 weeks is it, right? So that's how much I give you. Again, university is not like primary school anymore. So you need to manage your own time, right? I can only know what is happening in CS2040S. I cannot optimize for all the courses that you are taking. So it's impossible for me to do that. So I will release on 2 weeks. Okay, that's a lot of time really, because we really try to keep to the 4 to 5 hour kind of timeline, right, for the average student. So there are some complaints about Catis. This is it. Not being to see what went wrong really makes debugging a very big pain. I don't like binary pass fail. Expected output, not output. Okay, so a couple of things about Catis. I cannot actually change Catis code. It's some commercial software, so I can't really change it. But it does point out that this student is great. Actually, this would for us to think about all test cases. I completely agree. Test cases are very important, but maybe that's not permeating well. So I think that I will discuss with the TAs to focus some parts of the GG's maybe of tutorials on constructing test cases. Although Catis is binary pass fail, our grading is not binary pass fail. Okay, so if you make your way through most of the problem, but you're failing on 1 or 2 test cases, you don't get 0. You actually get partial credit. Okay, and I think that we'll be quite generous partial credit. We haven't released the partial credit scores yet because actually it's quite hard to grade some parts because the test cases are quite esoteric for you. We want to make sure that we have to look through your algorithm. We want to make sure that you're almost there and you're just missing 1 or 2 things, and then you can get a good score. Okay. There was a few comments actually about PS3 on a different website. That's true. PS3 is on a different website. The reason is that we had to do it. We actually tried to get it on Catis, but you couldn't do it because the test sets for PS3 are very, very large. They're like gigabytes in size. So we actually couldn't get it to work on Catis, but the PS4 or 5 will all be on Catis. Okay, so we'll be back on Catis. It just was simply we couldn't technically do it on Catis. Okay, so most people are finding tutorials and DGs quite useful. Some people are not, and I actually fed all your individual feedback to your TAs. So I split them up by your TAs and I send them to your TAs. And all your TAs have received your feedback and they'll be making changes in order to improve the DGs and tutorials. If you find that they're still not helping you learn, please let me know. Okay? So overall, I think most people are enjoying CS2040S, which I'm happy about. There are a group of people who are not. Okay, so if you belong to the 11, 12, 13%, I'm not doing something right for you, so I'm going to try to improve. Hopefully the changes that we're making will improve things. If not, please just send me an email, right? We'll post it on University of Piazza if you try. Let me know what has to be changed to make things better. My goal, as I said before, is not to help the best students. It's really to move everybody, maximize your potential. So whatever grade you're supposed to get, I can try to push you as far as possible to getting 100%. Okay, so that's my goal. Okay, so there's room to improve, like the majority of the class. So keep doing things better. Okay, speaking about doing things better, PS4 has been released. There are only 4 graded problems. There are a lot of practice problems for PS4, and the reason is that we got some feedback from our process about how you guys, feel as though you're not getting enough practice. So we released a lot of problems, and they're designed to help you get some practice. Okay. The TAs have also prepared a pre-PS4 practice sheet, and that's on Piazza. So please do that. That will help you to answer the questions a little bit better. Okay, so please have a look at this. Okay, so these questions, as I mentioned, we'll start doing whole everywhere questions. Alright, so if you go, let's test this out. I've never tried this before. So if you have any questions about any administrative issues, please in. If you don't have, let's just test it out. You can say no questions. Just post it inside so that I can see whether this works or not. Okay, is this working? Oh, no, this is no questions. Okay, great. Anybody has questions? No questions. Okay, thank you. All right. So this works when yes. Hello. Okay. 2 of you. All right. So why don't we get started? Oh, it's actually for sorry, that's a good question. Is 2040S bell curve? The answer is it actually depends. So I try not to bell curve unless it's necessary. Very often I find in large class it becomes necessary. Okay, but what does it mean by become necessary? It's all recorded. So I try to make it balanced and make it fair. So bell curving is usually the case where my exams are too difficult, and then you need bell curving to make sure that you're graded fairly, right? Okay, let's one by one. So many questions. Okay. Let me see this. Okay. So where's Alfred? Alfred is not here at home. Can you kill me? No. 4 to 5 hours for the whole lab or one question. It's for the whole thing.
I think I on my computer open BSc about 1 hour.
The grades be out. Which grades? Which grades? Quiz 2. Quiz 2 is already out, so we'll be fine. Extend deadlines. So, okay. So let's pause this for a while. Okay. Extension of deadlines. I'm not extending deadlines. The reason is that we have the late policy, right? So the late policy, you guys know what it is, right? You can submit on the last second of the last day of class. That's fine, but you get a penalty. You get a 60% penalty. Right? So, right? You can still submit even after the ends. Right? There are solutions for tutorial questions. Great tutorials. Yeah. So okay. Are there solutions for tutorial questions? Yes. Okay. We'll try to move if it becomes necessary. Chichen is not here. Okay, so let's carry on, or else this will continue forever. I think there's a lot of material today. So I'm going to do a quick recap of what we covered last week. All right. So what did we cover? We covered shortest paths, development for algorithm, and the relaxation method. And the relaxation method, we covered something called the path relaxation property, which was very important for proving the correctness of development 4. Okay. Now I think that I got a lot of questions after the lecture. So I'm going to go over things again from a slightly different perspective, and maybe that will consolidate the material. So remember what a simple path is. A simple path is simply that there are no cycles. Okay, there are no cycles. So if a graph contains no negative weight cycles, then the shortest path from some source vertex to some other vertex B is a simple path. Okay, no cycles. So this means that the shortest path can have at most how many edges? B minus 1, correct? There are no cycles. Okay, so at most is B minus 1 edges. Okay, so keep this in mind. Okay, keep this in mind. Okay, only B minus 1 edges. So then we said, or maybe after looking at triangle equality, we said, oh, there's this something called relaxation, this function. And relaxation is a very simple idea. It says, look, we're going to test. We're going to test whether the best way to get from some source node to some vertex is through some other node. Okay. If it is, then I'm going to update my distance estimate. If not, then I will just leave it. Okay. And the distance estimate here, dB, right, for example, is just your current estimate of what the shortest path is, the shortest distance is. Okay, the distance is. So, for example, if this is my graph, okay, this is my graph. Okay, this is after some amount of relaxations. Okay, and I want to update. I want to relax this edge. Okay, from A to B. I'm going to relax AB. Okay. So what happens is that I'm going to look. I'm going to see. Oh, what is the distance? Current distance to B, which is 5. Right? And is it greater than going through A? Okay. Should I go through A and then take one hop from A to B? So let's check. Distance to A is 3. A to B is 1, and this is 4. And it is better, so I'm going to update my distance. Okay, so this says that look, my current distance estimate, my current shortest path distance estimate is wrong. It's too large, so I need to shrink it. And the way I shrink it is by going through this other node A, right? Okay, so then we looked at path relaxation. So path relaxation is actually not a complicated concept, right? It simply says this: if there is if I tell you what the shortest path is, I tell you, okay, you don't define it, I tell you what the shortest path is. If you do the relaxation in order of the path, right, it will tell you what the distance estimate is. And this is very intuitive, right? So for example, if you have some source node, so I'm just drawing some graph. Let's say it's 1, 1, 5, 6, 5, 6, let's say. So all this says is that if I tell you what the shortest path is, so here the shortest path is SAT, set. If I tell you SAT is the shortest path, okay, this is the shortest path. What you need to do to get the correct distance estimate at T, okay, from source to target, is simply to relax this edge first, followed by this edge. Now, knowing what you know about about the relax operation, this has to be true, right? What you're doing is simply this. Your initial distance estimate at S is 0. The rest is infinity, right? To start. And so I'm going to relax this edge first, so this edge, right? Now I'm going to see, current distance is infinity. The best way to get is through S, right? So I'm just going to relax this edge, and this is going to be 1. Okay, and then I relax the next edge in order. So this is AT. Right, I relax this edge, this edge, and once I relax this edge, this will be 2. Right, this is 1 plus 4. Okay, so it's very intuitive. It's just that look, I'm just going to relax it step by step, right? Which is equivalent to actually just summing up all the weights, right, on this path. Okay, so that's the idea. Now, path relaxation says one additional thing, which is that this property holds regardless of any other relaxation steps that can occur. Why is this true? It's because of the if condition in the relax operation. So there's this if condition here, right? So if the distance is larger, you never update the distance estimate. Okay, so no matter what your relaxation operation do, because this is the shortest path, right, you will never get updated. Okay, so that's the idea. Now, let's look at this. If you know the shortest path, path relation tells you how to compute the distance. That's the idea. So here, given this example, what is the shortest path? It's tired. Must be easy. Okay, what's the shortest path? Someone yell it out. What's the shortest path here? From source to target, S to T. S. What's the next node? A, then then t. Great. So that's the shortest path, right? So to compute the shortest path from S to t is very simple. All you need to do is just relax the edges in order. So you just relax this edge first, this edge, and then this edge. Okay? If I tell you what the shortest path is, okay, I tell you in advance. So just imagine that I'm some genie and I tell you what the shortest path is. So you relax this one first, right? That gives you 2, and you can repeat this process, and then you get something like this. Okay? So initially, if you relax in order, the dt, which is the distance estimate at from S to t, will be infinity for two iterations, and then you get correct at the end, right? Because you're updating one by one. All right? So this is if you know what the shortest path is. But in general, we don't know what the shortest path is, right? We don't know what the shortest path. I told you, but in general, you don't know. So how do you use path relaxation to solve your problem? So that's where Bellman form came into the picture. We said that path relaxation holds, this property holds regardless of any other relaxation step. Doesn't matter, right? How many relaxation steps you do, it'll still work. So instead of relaxing things in order, we don't know what the order is. So we're going to relax all the edges at each iteration. Okay, so iteration 1, we're going to relax all the edges. Iteration 2, we're going to relax all the edges. And iteration 3, we're going to relax all the edges. Well, why does this work? Because if you relax all the edges, at some point you will cover the correct edge to relax, right? So you relax this one first. At iteration 2, you must relax this one. At iteration 3, you must relax this one. So that's why Bellman form works, because it doesn't matter how many other relaxation operations you do. If as long as you cover all the edges in one iteration, you are bound to hit the correct edge. Okay, and the benefit of this also is that okay, sorry, let me get the next one first. So the next question is how many iterations will definitely cover the correct order? So here I've done 3 iterations, but you need 5, you need 2. How many iterations you need? V minus 1. Okay, so again it's back to simple paths. Or the shortest path can only have V minus 1 edges. Okay, so that means that I only need to repeat these iterations for V minus 1 iterations. Okay, so that's the idea. So you repeat all and then you only do it for V minus 1 because the shortest path, the longest shortest path can only have maximum V minus 1 iteration, V minus 1 edges. Okay, remember that because you're repeating all the edges per iteration, this has a nice side effect. It doesn't just compute from S to T, it computes from S to all other nodes. Because what's the longest shortest is V minus 1, you're doing it, all the orders are covered here. All possible orders are covered here, right? So you are guaranteed to get the shortest path from S to all the other nodes in the network. Okay, that's why it's called single source shortest path. One source, shortest path to all the other nodes. Okay, so this is we're coming Bellman form again because, like I said, it's the grandmama for all the other methods that we are seeing, and it's very important that you understand this method well. Okay, so let's do some quick questions. Okay, just to make sure everybody understands, because this is very important. If you are okay about Bellman form, it's fine. If you have any questions, please post them now. I'll wait like 30 seconds. Okay.
Yeah.
Are we good? No responses yet. Oh. What if one node has 2 one-way paths to 2 other nodes? 2 one-way paths to 2 other nodes. Okay. So I think your question will be answered today. All right, about 2 one-way paths to 2 other nodes. Okay, we'll show that in a second. Can I release the DG solutions? So, so this is when I was in undergraduate student. I got this question. I asked this question to my professor. You know, he said to me, "You want DG solutions? Go for DG." So we will release DG solutions, but at the DG, I mean that's the point, right? You go there, you're supposed to discuss the problem sets. If you want to know specific solutions, please just post on Piazza. Okay, post on Piazza. We'll do that. My name is today. Okay, fine. Then we will do that as well. So just post a question. Just post a question. Why is DT infinity at the first 2 iterations? That's a good question. So let's look at it. So remember that when we're running Bellman form, what do? We first set all the distance estimates to be infinity. That's our initialization. Okay? We first set distance all to infinity. That's why they start off at infinity. Then later you update them as you go. Why? Because infinity is the largest possible number. Alright? Also, it captures the case where you cannot actually get to t from s. Right? If your graph is disconnected, for example, then your path is actually infinity because there's no way to get there. Alright? Okay, so let's move on. Okay, so this is Belmont forward, right? It's very simple. From I1 to n-1, we just relax all the edges in the graph. So the question we're going to deal with, and we saw it last week, is what we're doing again today, is in what order I should relax the edges. So Belmont forward doesn't specify what order, it's just any order, right? And it doesn't affect the algorithm, right? But if you're a bit smarter about the way you relax the edges, in certain special cases, you can actually get better algorithms than Belmont forward. Okay? So we took a look at trees last week, and in trees, remember the definition in the graph context is that every node only has one parent, okay, except the root, which has no parent. Okay? And in special case for trees is that OV equals to OE edges, because every parent only, every node only has one parent, okay, one child to the parent. So in this particular case, what order should you relax the edges in? Do you remember from last week? What order? BFS or DFS order, right? So you can relax in either way, and you can run it on OB time. Okay, so this is a special case. Okay. Today we're going to look at no negative weights, all right? And we're going to learn about Dijkstra's. So before we get to Dijkstra's, I'm going to show you some other properties first. All right. Let's start off with the example. There's a problem. So a couple of students came up to me after lecture last week and said, "Oh, how can I store the shortest path?" And this is a great question to test your understanding of how Belmont forward works. Okay. So this is the question: how can I store the shortest path? Okay. So if I give you this is my shortest path algorithm now, Belmont forward. How can I? When should I store? How can I store the shortest path? Any ideas? So do you remember BFS, DFS, how we stored the shortest path? What do we store for BFS and DFS? When you visit a node, what did you do? You store where the parent, right? How do you get there? Right? So you store your parent node, right? How you got there, right? H2, right? So you store that. Okay. So leveraging on the idea, for Belmont forward, when should I update where I came from? Where should I update who my parent is? Yeah. So over here, as soon as my distance estimate improves, it tells me that, oh, there's a better way to get to me. The better way to get to me from S is to go to some other node, right? Is to get to W and then W to B. So here, as soon as this becomes true, I need to update where I'm coming from, right? That's the test. Okay. So all I need to do is just add, update my predecessor or parent. Okay. So this constructs something called a predecessor subgraph. Okay? A subgraph, if you remember, is just a subgraph of the original graph, right? So it contains a subset of the edges and vertices. Okay? And this predecessor subgraph basically stores where each node, like where you come from on the shortest paths. Okay? It stores your parent on the shortest path. Okay? So that's what it does. So for general graphs with no negative cycles, the predecessor subgraph actually forms a tree. Okay, it forms a tree. So remember what a tree is? The tree is that you only have one parent node or one predecessor. Okay? There's not two predecessors, there's one. Alright? It forms a tree. Okay? Except for the root, of course. Now this is true because of that. It's true because the subpaths of shortest path are actually shortest paths also. So why is that the case? So let's look at this shortest path. Okay? From S to D. Alright? So the claim is that if the shortest path goes through some value x, right, S to x is also a shortest path. Okay, so that's the claim. If this is the shortest path from S to D, and it goes through some node x, the claim is that this S to x is also a shortest path. Now the reason why this must be true is that imagine that there is another shorter path to x. Right? What you can do then is take this path and then go to D. And that would be shorter than this path through X. Right? Like this. So it must be the case that this forms a prefix to the shortest path, and this shortest path is contained within this one. Okay, so there is no other shorter path, right? You get a contradiction. Okay, so this is how the predecessor subgraph property is stated more formally, right? It just says formally what I said before. Once your distance estimates are all correct, essentially, then the predecessor subgraph is the shortest path tree rooted at S. Okay, this only happens once all your distance estimates are correct. Okay, so after you run Bellman-Ford and it's done and you know negative cycle, then you construct your predecessor subgraph and it will form a shortest path tree. Okay, this means that to get to any node, there is just one parent from there. You follow it all the way back. Okay, so I hope that answers the earlier question. All right. So Dijkstra's algorithm leverages this idea to an extent, right? The key idea is to kind of relax the edges in some correct order, all right? And we're only going to relax each edge once, only once, okay? Compared to Bellman-Ford, where each iteration you relax all the edges. Here you're going to just relax each edge once. So I'm going to cover how Dijkstra works. First, we'll cover a little bit about Dijkstra. Okay, so this Esker Dijkstra, he was a famous computer scientist. Okay, and Dijkstra said many interesting things. All right, he was known as quite the character. All right, so he would say things like computer science is no more about computers than astronomy is about telescopes. The question of whether a computer can think is no more interesting than the question of whether a submarine can swim. There should be no such thing as boring math. Elegance is not a dispensable luxury, but a factor that decides between success and failure. So this is some of his nice quotes. There are some, simplicity is a prerequisite for reliability. I like that as well. So there are some rather weird quotes. So he says things like, it's practically impossible to teach good programming to students who have prior exposure to BASIC. BASIC is a programming language you guys don't learn nowadays, but I learned it when I was a kid. As programmers, they are mentally mutilated beyond all hope of regeneration. So don't learn BASIC, don't learn BASIC. Right? So how many people here have seen BASIC, the algorithm, the programming language?
Yeah,
okay, so you guys are mentally mutilated. Okay, the use of COBOL, which is another old programming language, cripples the mind. Its teaching should therefore be regarded as a criminal offense. Object-oriented programming is an exceptionally bad idea, which only could have originated in California. He also had an unconventional teaching approach. If you think my teaching approach is unconventional, he would invite students to suggest ideas, then he explored or refused to explore because he violated some of his tenets. He conducted his final examinations orally over a whole week. I can't do that in this class, whatever. Each student will examine in Dijkstra's office or home, and the exam lasted several hours. Okay, he would just basically grill them for several hours on questions. So that's Dijkstra. Dijkstra was quite the character. He would, yeah. So Dijkstra's algorithm is very much like Bellman-Ford. Okay, like I said, Bellman-Ford is a grandmama. So Dijkstra algorithm is based on that. You're going to maintain a distance estimate again for every node. We are going to start off with the empty shortest path tree. Remember, I said that first subgraph forms the shortest path tree, and we're going to start with an empty one. Okay. So what we're going to do is we're going to consider the vertex with some minimum estimate. We're going to add that vertex to the shortest path tree, and then we're going to relax all the outgoing edges from that vertex. Okay, so let's see an example. I think an example will make things more concrete. Okay, so we started S. Okay, we started S. So I'm going to put S in my. Remember the distance estimate S is going to be 0. Okay, everything else is going to be infinity. And so I'm going to add the source. Okay, which is S. And then I'm going to remove S and then relax all its outgoing edges. Right? This should seem a bit familiar because we did answer algorithm. Remember, we were finding the values of edges. You should take out and remove all the outgoing edges. So this is instead of removing, we're relaxing all the outgoing edges. Okay? So we relax all the outgoing edges. When we relax the outgoing edges, we are going to update. Basically, it's the target of all the outgoing edges. Okay? And then we're going to add that to our data structure. Okay? So, for example, SA, I'm going to, if initially it was infinity, I relax SA, then the distance estimate for A gets updated to 5, the distance estimate for G gets updated to 8, and distance estimate for D gets updated to 9, right, from infinity. That should be quite easy to see now that you understand the relaxation operation. So now what do I do? Now I'm going to look here, all right? I'm going to find the minimum estimate, the node with the minimum distance estimate, okay? And here it's going to be A, right? A has distance 5. So I'm going to remove that. Okay, I'm going to remove A from this data structure, and I'm going to relax all its outgoing edges. All right. So when I relax its outgoing edges, I'm going to update C, B, and G. All right. I'm trying to update them. So C is going to be 5 plus 15. That's going to be 20. This is 5 plus 12. That's 17. Right. And this 5 plus 4. 5 plus 4 is 9. 9 is larger than 8, so I'm not going to update my distance estimate for G. G remains the same. Right? Remember the relaxation operator only updates if the new distance estimate through A is smaller, so we don't update. So we're going to look at the next smallest item here, which is G. Okay, so I take out G and I relax its outgoing edges. I'm going to try to update B. All right, nothing happens, and then I try to update. Update B, which improves the distance estimate. It's from 17 to 15. Okay, 8 plus 7 is 15. Okay, so I drop my distance estimate for B, and then I update B. Okay. So I repeat this process again and again. I'm sure by now you understand the process, right? You just remove the minimum distance vertex, and then you relax all its outgoing edges. All right. You repeat this process again and again and again until you are done. Okay. You remove the final node and relax. There are no outgoing edges, so you don't have to relax anything. All right. When you're done with this, all these distance estimates are correct. Okay. You are done. Okay. So then you have your shortest path tree. Now notice that I don't relax all the edges at each iteration. I only relax the outgoing edges of the minimum distance estimate vertex. Right? I take the one with the minimum distance estimate, and then I relax its outgoing edges. I don't relax all the edges. So this is the source code for Dijkstra. Okay. So what I do is I create a vertex set. For each of my vertices in the graph, I'm going to set its distance estimate to infinity, and I set its previous node to undefined. This is the predecessor or the parent node, right, to undefined, which means I don't know. I'm going to set my distance for S to be 0, right, because this is the source node. And while this data structure Q is not empty, I'm going to get the minimum distance vertex in Q. I'm going to remove it from Q, and I'm going to relax all its outgoing edges. Okay, so that's what I'm going to do. Here's the question. So what data structure or ADT should I use for, let's say ADT. Which ADT should I use for the vertex set Q? Should I use a stack? Q, list, priority queue, okay, priority queue. So the answer is priority queue. Why priority queue? Look at the operation that you're performing. We're always trying to find the vertex with the minimum distance estimate. Now you know that the data structure, or the data structure you use for it usually, right? But the ADT is a priority queue, right? The priority allows you to find elements with the minimum key, right? Very rapidly. When you do relaxation, however, you may have to update your distance estimate, all right? Now heaps. You've probably covered this in DG already. If not, you know that heaps, at least in Java, don't allow you to update keys very efficiently. Okay? So you need to do things like update your distance key, which is decrease your key. So typically we use AVL trees. Okay, so one way to do this is to have an AVL tree, which allows you to do your decrease key quite rapidly, all right, in log n time. This is all log n, right? So you know AVL trees well by now. It's all log n. Here's a question: can we quickly find how quickly can we find a node, right? So that we can update its distance, let's say. So how can you quickly find a node in a tree? So if you use the tree by itself, you have to run contains, which takes O log n time. Is there a faster way? What's a faster way to look up something? Hash table. So you use a hash table. So one way is to use hash tables to map, right, from a key to some node structure in a tree, for example. So you just have the node labels, right, the node keys, and then the reference to a node in the tree, okay, in the AVL tree. So that's a good way that you can do lookups, and that can reduce your contains down to O1. Okay, O1 is time. Okay, so some of you have covered more advanced data structures during your discussion groups. This is where it comes in handy. If you use the ABL tree, everything is log B, and we will just assume that for the rest of this lecture, or even in the finals, I'm just going to assume that you're using the ABL tree unless you specify otherwise. Okay, but ABL trees don't give you the best performance. The best performance actually comes from something called Fibonacci heap. So you guys have seen binomial heaps hopefully, and some of you may have seen Fibonacci heaps as well. Alright, so Fibonacci heaps can give you better performance here, right? Especially if you look at the insert and increase key, expect that it's O1 is okay, so you can get much better performance with Fibonacci heaps. Okay, so Dijkstra algorithm, the analysis should look familiar by now. Okay, so we're going to do insertions and delete bin B times. Okay, because each node is only added to the priority queue once. You never add a node again. Once you take it out, you relax all its edges, you never care about it again, right? So it's only added B times. And then for each node, you relax all its outgoing edges, right? And that returns E times, right? So because of that, and you know that priority queue operations are log B, because we're using our ABL tree, the total time is going to be B plus E log B. So that's the total time for our Dijkstra's algorithm. Alright? If you use Fibonacci, you can get slightly better time, but for most part, we just assume ABL tree. Okay? Alright, so it's B plus E log B. Alright, so that's Dijkstra's algorithm. So now a question might be, well, I know how Dijkstra's works. I know the time. And the time is, this time is better than Bellman-Ford. Okay? What's Bellman-Ford's time? Right? Each iteration you relax E edges, you run from B minus 1 iteration to BE. This is much faster. Okay, it's V log B plus E log B. Right? This is much faster. So the question is this: why does it work? Right? Why does it work? So the proof is actually by induction. Alright? I won't cover the whole proof today, but I will give you a good visual kind of visual insight into what is the key idea behind the proof. Alright, and this is by induction. So induction, the key idea here is that every finished vertex has a correct estimate, and although the initial the initial finished vertex is the start, once we assume the inductive hypothesis and go from there, we will see that eventually all the estimates are correct. Okay, so that's the idea. So let me show this visually. Okay, so let's draw this out. Let's start here. It's a little bit better. Okay, so imagine as when you start off, right? You have some start for this. Okay, and this is the the set of all the finished vertices. Okay, in your finished vertices, you assume that the distances are already correct. Okay, by induction, so you assume that the distances inside this set, they're all correct. Okay, now we're going to take some vertex out of our priority queue. Okay, we're going to take some vertex V out of our priority queue. Now I want to show that the distance estimate after you take it out and put it into this set will be correct. Okay, that's my goal. So we're going to label the distance to V. All right, we're going to call it dV. Right, so remember this, dV is the distance to V. And now I'm going to sorry, let me put this back. Okay, so V is going to be our fringe vertex. Okay, we're going to take it out of priority queue, put it into the completed set. Now I'm going to assume that the path estimate is not the shortest, the correct path estimate is not the shortest path. Okay, I'm going to assume that's the case. Right, let's say it's not the shortest path. We're going to show contradiction. So if it is not the shortest path, then there is some other path, right, that takes me to V. Alright? So instead of taking V out and connecting with this edge, I assume that there's some other path. Right? There's a real shortest path to V. So on this path, there must be some W, which is fringe vertex. Okay, fringe vertex means in the priority queue. Okay, it's in the priority queue. And let's assume that we label the real path distance as RV. Okay, so there's some other fringe vertex W, right? It's rather than V. And to get to V, actually the shortest path is this way. Right? We assume that's the case, and we'll show a contradiction. Okay, so if this path P is the shortest path to V, then the prefix of P is the shortest path to W. We know this why? Because shortest path contain other shortest paths. right? So we say that if this is the real shortest path, then this has to be a shortest path as well, right? So that means that this distance is accurate. Remember, because we have relaxed this edge, right? We have relaxed this edge before we add it to the property Q. Now, because of this property, we know that the distance to W, right, must be less than the distance to RV. This is RV, right? This is RV. Distance to V going through W. Now this has to be less than dV. dV is the distance direct to V, right? This path, let's say. Okay? Because we said that P is the shortest path, right? Now, but this cannot happen. Why this cannot happen? We have already seen a contradiction because the distance W is bigger than the distance to V according to the priority Q. Right? The priority Q this is supposed to be removed from the priority Q, right? And we said that there's some other path that leads to V, right? That we're showing this cannot happen. This cannot happen because this priority Q says that the distance to V is already the smallest possible. Okay, it's already the smallest. Okay, so you have a contradiction. This line, right, is incompatible with this line. Okay, so here it says that this path, right, this distance to W must be smaller than distance to V. But your priority Q says that your distance to W must be greater than distance to V. So this is a contradiction because of V is the minimum in the priority Q. So the claim must be true. Right? The claim must be true. The V is the thing that you take out, and once you add it to your finished vertices, the distance estimate is correct. Okay? So the inductive step holds, and we're done. Alright. So this is how it works with non-negative weights. What happens if you have a negative weight? What goes wrong? So the proof only works when there's non-negative weights. When you have negative weights, something bad happens in the proof. Okay? What happens is that this line no longer becomes true. Why? Because you can have negative values here. Right? You can have negative values here. So this may not be true. The distance of U is less than distance to V. Okay, so your proof breaks down. So you actually cannot do Dijkstra, right, if you have negative edges. That's why Dijkstra only works for cases where the edges are non-negative. Let me give you an example. So here, imagine that A, we're just going to remove A. We've already done S, okay, and we've relaxed these two edges, okay. Now we remove A, okay, the distance estimate to A is 4, so it's smaller in our priority Q, we take it out. We relax A and then we mark it as done. So we never look at it again in the context of Dijkstra, right? So then we continue on, we relax A, we relax its outgoing edges, right? Now we remove B. Okay, when we remove B after some steps, when we remove B, we realize that, this thing is incorrect. This 4 is incorrect. The shortest path to A is not here, but here, right? From 10, -9 is 1. Okay, so I need to update A again. I cannot just update A once, right? I need to actually do this process again, which is why negative weights really throw a wrench in how Dijkstra works. Okay, so Dijkstra cannot work in negative edges. So maybe one way to handle this is, hey, we have negative edges, why don't we just fix the negative edges? Let's remove the negative edges. And one way to remove negative edges is let's just add a constant. So we find the largest negative edge, okay, and then we just add some constant. Right? We add the constant to offset the negative edge. So for example, if you have 4, 10, -9, like in the previous case, 4, 10, -9, I'm just going to add 10 to every edge. Okay, I add 10 to every edge. Now there are no more negative edges. And I run Dijkstra. Question is, can it work? What do you think? This work? Now if you think that this can work, put down yes. If you think it can't work, put no. And if you think it can work, try to convince yourself it can work, like come up with a proof. If you think it cannot work, then give me counter examples, right? What situation does it fail? Okay, so I'll give you 30 seconds for this. Check with your friend. Close contact, so check with your friend.
Of course, negative makes it better.
I'll wait till 20.
I think I can maybe. Seems to be Dijkstra thing again. Just find the shortest. Step 1, remove A, relax A, mark B.
most of you have said yes, this can work. Some of you have said no. So half of the response. That's 33%, sorry, I said no. 40. Alright, so let's have a look at the solution. So if you answered yes, you're wrong. Okay, it won't work. So let me give you an example why this is the case. Right? So what's the shortest path to A? What's the shortest path to A? This is through B, right? This is 1. This is 4. If you just go through here, it's 4. Alright? So whatever operation I perform on the graph, better maintain this the result. Okay, the answer should be correct. The problem is that when I add 10 to everything, notice that my shortest path along this route, the distance around this route has changed. It's become 21. On this side, it's dropped to 14. Okay, it's 14. So the shortest path is no longer preserved once I do this operation. So this is not going to give me the correct shortest path estimate. Right? Remember, the true shortest path is this. After I do my reweighting, it's going to tell me this. This is wrong. Right? This is not the shortest path. Okay, the graph. So I'm not allowed to just add some constant to all the edges and then run the extra algorithm. That won't. Okay, that will give you the wrong shortest path. Okay, so if you want to see, have a little more like view of how the algorithms are connected, you notice that the algorithm that we just saw by extra is not so different from things that we've seen before, particularly BFS and BFS, right? So in BFS, we look at the vertex that were discovered least recently. In DFS, we extract the vertex that was discovered most recently, and Dijkstra's extracts the vertex that is closest to the source. Now, if you look at the algorithm structure, they're very similar. The only difference is actually that we are changing the data structure that we employ, or the ADT that we employ. In DFS, we use a queue. In DFS, we use a stack. In Dijkstra's, we use a priority queue. Alright? So the algorithm is quote unquote the same, right? That the structure, the overall structure is the same, but the behavior is very different. The behavior is very different because of these underlying data structures. Okay. All right. So that's to summarize Dijkstra. The basic idea is that again we just maintain some distance estimates. We're going to find the unfinished vertex with the smallest estimate in our priority queue. We relax all its outgoing edges, and then we say, okay, I'm done with this vertex. The distance estimate is correct. Okay. And if you use AVL trees, then you get this very nice runtime, which is better than using Blue-bound forward. Okay? The constraint, however, is that you cannot have negative weights. If you have negative weights, don't run Dijkstra. I see this, sometimes I ask Dijkstra on the exam or quizzes, and okay, invariably one of the students will say, run Dijkstra when it's very apparent that there can be negative edges. So if you ever want to run Dijkstra, make sure that your graph has no negative edges. Okay? And you can't just add a constant and expect things to be done. Okay, so we've covered 4 of these already now. We've covered Belmont BFS, we covered Belmont and 3 of these special cases. There is one more special case, which is the directed acyclic graph, right, the DAG. Right? And the way we're going to do this is via topological sort for it. Right? So before we go into that, can we just get a quick question on Dijkstra? So if you have any questions about Dijkstra, now's the time to put it on board everywhere, and we'll try to answer them. Okay. Why AVL tree not heap? That's a good question. You can use a heap. All right. The problem is that if you just heaps, then you have to do this decrease key. You have to update your key. So remember when you do a relaxation operation, you update distance estimates. Right? So when you update distance estimates, then you're going to revise the key and you're going to have to push your element around. And this can be inefficient, so use AVL tools. Right? With uniform graph cost, that's right, equals to EX. That's actually right. Yeah. Okay. So if you use a Q, right? Okay. Regarding weighting, how about deducting the constant after calculating the half? That won't be correct because that still won't be correct. Okay, you can work that out. Are negative theoretical or do they exist in the real world? Right? Negative edges do exist. right? So an example is that I want to find a route from, let's take a route finding in a city, let's say, okay? So negative edges would be, for example, if my positive edge is how much petrol I use, okay? And if I pass through a node which has a petrol station, I can, at a certain edge in the petrol station, I can refuel, okay? So I add fuel back, that would be a negative edge, for example. Right? So positive edge because I want to minimize, right? And then positive would be like fuel consumption. I don't understand why we look at the node with the least distance in the queue first. Okay, the reason why you look for the node with the least distance in the queue first is because its distance estimate is going to be correct. Right? Its distance estimate is going to be correct. And we proved this a while ago when we were looking at the proof of Dijkstra. Right? We're saying that for all nodes that have not been finished yet, right? In the fringe nodes that are in the priority queue, you want the one with the least distance because that's the node that has the correct distance system. Fringe node. So the fringe nodes are those in your priority queue. You can think of that are connected to other nodes in your finished set. Okay? In your finished set, right? There are outgoing edges, the other nodes. So those nodes are the ones that are in your fringe. What is the preset of P? What do you mean the preset of P? Oh, prefix. Prefix of P, you mean prefix of P. So prefix of P is, let's say you have A, B, C, D, E, right? A, B, C is a prefix of A, B, C, D, E, for example. Okay, it's just the beginning part. Right? Okay, any more questions? This is working out well, I think. Okay, what if the fringe node with the least distance leads to some large weight? Okay, so it can lead to some large weight, it's fine, but it doesn't matter because remember that whenever you update your node in the priority queue, you're going to relax all your outgoing edges and you're always going to take the node which has the minimum distance, right? And we know that from our earlier analysis that the shortest paths contain other shortest paths. So if you lead to some large node, for example, it doesn't matter because we'll add some other fringe node in the next iteration. Okay? And if the fringe node has a smaller distance estimate to your target node, we're going to use that. Okay? So this is a good question because you're asking about whether shortest path trees are unique, right? So this is a good question. How many people here think that shortest path trees are unique? You think shortest path trees are unique? That means there's only one possible shortest path tree. And when you run Dijkstra, of course you get the shortest path tree. So the answer is that shortest path trees are not unique. Okay? We'll learn something called minimum spanning trees later. They are also not unique. Alright? So there can be multiple shortest path trees. Alright? And you can convince yourself of this by constructing a few examples. There are some trivial ones. There's some non-trivial ones as well. I encourage you to try to construct some examples. I'll tell you the answer in advance that they are not unique. Okay? You can have two shortest path trees for the same. Alright, so let's move on. Alright, so remember what is a directed acyclic graph? So directed acyclic graph or DAGs have no cycles, right? Alright, so the way we are going to solve, find the shortest path, single source shortest path on a DAG is to first use topological sorting to get an ordering of the nodes, and then we're going to relax them in order. Alright? So for example, if this was my DAG, I first do a topological sort. Okay, so it's in this order. Okay? And what I'm going to do is I'm going to relax the edges in order. Okay, so I take S, I relax all the edges, outgoing edges, I take the next node, relax all the outgoing edges, and I go in this order. Okay? So I take S, I relax all the outgoing edges, and then I update my distance estimates. I take the next one. Alright, this is not like Dijkstra. Okay, I'm not going to take my minimum distance estimate node. Okay, I'm just going to take them in order. Alright? I take this node, I'm going to relax all its outgoing edges. Again, this will update this node to be 14. So previously is this. I take this out and I relax its outgoing edges. This will be 14. Before next, that's going to update to 5. I'm going to do 3. 3 changes this to 8. I do 5. Again, I update this because I relax the outgoing edge. And then finally I do 7, which has no outgoing edges. Okay? So key concept is simple. I do topological sort, which you guys know how to do. You know 2 ways of doing it. And then go relax them in order. So the question you might have is, how come this works? Why does this work? Right? Why is it that I can do it in topological order and it's fine? The answer actually relies on path relaxation property again. Okay? It again relies on the path relaxation property. Now, look at this. Imagine this is your shortest path. Okay? When I do things in topological order, what am I guaranteeing? Right? On this, when I do things in topological order, I must, right, relax S before A. The source is always relaxed first, but that's fine. I will always relax S before A. I will always relax A before B, so I will do this H first, and I'll always relax B before D, right? Because it's in topological order, right? This means that I will relax the edges in the correct order, right? Because of the path that. And if I relax the edges in the correct order, I'm guaranteed that my distance estimate will be correct, and then I will get the shortest path. Okay? So path are relaxed in order, so distance is definitely correct. Okay? After relaxation. So that's why you can do things in topological order. Again, back to our path relaxation problem. Okay, so that special case again is very fast. It's just B plus E. All right, and then you can analyze it on your own. Right, it's straightforward. All right, so we've covered all these special cases. Right, we started off with the grandmama, which is thermal forward. We then looked at unweighted graphs, which we can just run DFS. Then we looked at non-negative weights, right? Actual algorithm, and tree, and then we looked at it on a deck, which was completely philosophical. Okay. All right. Here's a good question. So, if I give you a weighted graph with non-negative edges, okay, non-negative edges, I want you to find the shortest possible route, okay, that visits each vertex once. I visit all the vertices, so I visit each vertex once, and then I go back to my origin. Right? That's what I want to do. Okay? So, it's actually a pole everywhere, so let's go to pole everywhere. Sorry, somebody asked which node do you start with. You can assume that I always give you the start vertex. Okay? I always give you a start vertex. Okay, so we want to find the minimum distance cycle. The question is how fast can you solve this problem? Can you use down forward? Can you use BFS or DFS? Can you use Dijkstra? Or is this a trick question?
Trick question.
So you talk to your friend. Let's see. Remember, minimum distance cycle. I start in some node. I want to visit all the vertices, and I want to finish at my start. Right? I want to find the minimum distance cycle. Alright, so a lot of people are saying it's a trick question. I mean, everyone is saying it's a trick question. So let's have a look. Guess what? It's a trick question. Okay? Trick question is trap. Why? This problem you may have heard of before. It's called the traffic salesman. Some people here have heard of traffic salesman. You should have heard about it in take 151 or maybe from
Yes, good mate.
it's MPR or whether it's MP complete. Okay.
He write in the
NPR stands for NP stands for non-deterministic polynomial acceptable problems. Okay. They are very hard to solve, right? And you will learn about what very hard means when you get to 3260. Okay. I won't go into key detail here. But the dynamic program solution is about b squared to the power of b, so it's exponential in the number of vertices, which is not nice. Okay, this takes it's very hard to solve. Okay, but once you have the solution, it's actually quite easy to check that it's a good solution. Okay. Dijkstra, well, for all of them, they will work on this. Okay, this is not easily solvable using the techniques that you currently know. Of course, you can brute force it, right? When in doubt, brute force. So brute force, you try all possible permutations of the vertices. And that's n factorial. That's not a good idea. You can use the dynamic programming approach, which is exponential, or you don't bother solving this problem at all. So the point is here is that if someone asks you to solve traveling salesman, don't think that you can solve it efficiently. Okay? You can find good approximations, but to solve it exactly is very hard. Okay, and unless P equals to NP, you are likely to find an efficient solution. Okay, so if someone tells you to do this self-like type, okay, go do something else. Alright, the other NP complete NP hard problems, they're very fun to look at. Also, they're very important to know what they are. So if you can reduce your problem to an NP complete NP hard problem, then you probably don't want to spend your time trying to solve it efficiently because you're not going to find a better algorithm, a fast algorithm. Okay, you're not going to be able to do it in general unless you happen to do it, then you write a paper in the Wings and Turing Award and a Nobel Prize maybe. I don't know. So don't spend your time working on. Don't waste time trying to solve a problem which you know to be very very hard. Okay, but then sometimes you can try using use very efficient good approximations. Okay, to solve these problems. But we won't cover these. This is way advanced. You take in the next course. All right. Okay, so we've talked about special graphs. All right. We talked about Bellman Ford, but how you can specialize that by looking at the orderings. Okay. And all the algorithms are very similar. We just change the order, right? By changing the order, we get different behavior and better ranking. But in each case, we're restricted in some way. You have to make some assumption about whether all the edges are the same weight or all the edges are non-negative, right? So there are some restrictions that you have to take into account, right? Or whether it was a DAG, right? We also know how to analyze the computation complexity of that. Okay. So this was a summary. If you have any questions about any of today's material, let's put it on.
Put them on, Daddy.
Questions for a little bit. Okay, if anybody have any questions, no questions, then I'll see you tomorrow.